Hey, welcome to the second part of the video on applications of trig. Let's try to get our bearing on this one a little bit. So in the last one we looked at sets of double right triangles. Here we're going to talk a little bit about bearing. So bearing gives you the location of an object relative to a north-south line. So the bearing comes in three pieces. First, it tells you if it's above or below the x-axis. The second gives you an acute angle measure. The third one tells you east or west of the y-axis. So first of all, let's look at this guy over here. You're going from the origin in this direction. So it's got to come from the north-south line. So there's north. The question is, from the north, how far did you go and what direction? So this angle given is 40 degrees. So from the north, you went 40 degrees in which way? In the east. So look to see how the bearing is written. It's written as north 40 degrees east, meaning you started going north. Acute angle is 40 degrees. In which direction? East. All right, what if you went this way? Well, you could still think of walking up, right? You're walking up, you're walking up, you're walking up. So you're walking from the north 65 degrees, but in this direction, now you're going west, you're not going east. So this is how we would write the bearing, north 65 degrees west. All right, the third example is in the fourth quadrant. You're walking this way. So from the north, that would be more than 180 degrees. So instead of going north, what if we went south? Oh. So from the south, we can turn east 70 degrees. So it's given with an acute angle. So again, we can't go north and then spin all the way around. We got to come south and then go 70 degrees towards the east. All right, so the biggest advice I can give you for these things is draw a picture, because these get a little confusing if you're trying to do all this in your head. So you leave the entrance to a system of hiking trails. You hike 2.3 miles on a bearing of south 31 degrees west. Trail turns 90 degrees clockwise. You hike 3.5 miles on a bearing of north 59 degrees west. Whew, that's a lot of words. Let's try to draw some pictures out here. All right, remember here's north, south, west, east. So you start at the entrance. So let's consider the origin to be the entrance. You walk 2.3 miles on a bearing of south 31 degrees west. So from the south, you're going to head towards the west 31 degrees. Now it says the trail turns 90 degrees clockwise. Well, which way is the clock going? The clock goes towards the right. So if you're walking down this trail, you're going to turn towards the right 90 degrees. And you're going to hike 3.5 miles. The bearing there really is not as important right now, because if I tell you you're turning 90 degrees, you're turning 90 degrees. This one is 2.3 miles over here. So the first question is, at the end, how far are you from the entrance to the park? Well, that seems like a nice Pythagorean theorem question, because here's the entrance to the park. There you are. So you made yourself a right triangle where c squared equals a squared plus b squared. And now I just need to grab my calculator and solve this. All right, once you have the first part, then take the square root. And I get 4.19. So 4.19 miles. That's the distance here. Now the second question says, what is your bearing from the entrance to the trail system? So my reminder was that bearing is from the north and south. So first let's start with this angle over here. If I can find that angle over there, then I'll add 31 to it, and I'll get the number of degrees from the south. All right, so from that angle, let's use the two numbers in purple. Two numbers in purple are opposite and adjacent. So tan of theta equals opposite over adjacent. All right, so if the tan of theta is 3.5 over 2.3, then theta is the inverse tan. So take the inverse tan of 3.5 over 2.3, and that'll give me an angle measure. So let's try it. inverse tan 3.5 over 2.3. I get 56.7 degrees. Now, that 56.7 is the angle here. But from the south, I've got to go 31 degrees first, and then that 56.7. So take that 56.7 and add 31 degrees, and I get 87.7. So from the south, I've got to go 87.7 in the direction of the west. So there's my bearing. Right? So from the south, I'm going to go 87.7 till I get towards the west. You can't go from the north because then you would have to go more than 90 degrees. Remember, these bearings are acute angles, so 87.7 is getting close to a right angle, but it's not a right angle yet, so it still works for our problem. All right, another topic that shows up in here is simple harmonic motion. And the picture over there has a little spring, so you can picture taking that ball, pulling it down, and then letting go. And what does the spring do? It goes up and down and up and down. So we call the vertical distance the d-axis for distance. The zero mark is equilibrium. In other words, if you let that little weight hang off the bottom of the spring, didn't pull it, didn't push it, whatever it was when it just was hanging there freely, that's called equilibrium. All right, so here's a little picture of the spring. It goes up and it goes down. So that d equals -4 is me pulling the spring down, and then boom, let it go. And it goes up, it compresses, it comes back down. So when it gets up here, it's pretty compressed. Then it's really stretched out. Then it's really compressed. Then it's really stretched out. And down the bottom are the times. So 0 second, 1 second, 2 seconds. Look like 3 seconds is up at the top. 9 seconds is up at the top again. And back and forth, back and forth. So there's an example of simple harmonic motion. And so the formula that it follows is either based on sine or cosine. It can be either one. So the motion has an amplitude, right? How far from the equilibrium did it go? And again, we're considering the equilibrium. We're just letting it hang there. We're not pushing or pulling. So here's the equilibrium. How far did this thing go up and down? Well, it looks like the amplitude is 4. Then it says that the period is 2 pi over w, where the period gives the time it takes for the motion to go through one complete cycle. So how long does it take to go through one complete cycle? Well, it looks like it takes 6 seconds, right? It starts on the bottom at 0, goes up here at 3, comes back down here at 6. So in our case, it looks like the amplitude is 4, and then the period is 6. So if 6 is 2 pi, I'm just going to call it w. Then I can find w by multiplying both sides by w and dividing by 6. And so I get w equals 2 pi over 6 or pi over 3. All right, so the ball's on a spring pulled 6 inches below. Its rest position then is released. The period for the motion is 4 seconds. Write the equation for the ball's simple harmonic motion. So how do we know whether it's sine or it's cosine? Well, if you look here, this thing would be a cosine graph. Why? Because it didn't start at rest. If it had started here and went like up, down, back up again, that should look like sine. But if it's pulled down and then goes up and down again, then it should look like cosine. All right, so it looks like here the amplitude is 6. Because this one, instead of starting here at 0, is pulled 6 units below and goes up and back down again. Okay, so we assume that if it's pulled 6 units below, it reaches a max 6 units above. It says the period is 4 seconds. So if the period is 4, remember we said the period was 2 pi over w? So multiply both sides by w, and you get 4w equals 2 pi. Divide both sides by 4. 2 pi over 4 simplifies to pi over 2. All right, so we said we're going to use cosine because the ball didn't start at its rest position, so this is our function. How do we get that thing to start down, right? The picture we have here, normally cosine goes like this. But that's not what this graph did. This graph started on the bottom, came up and down again. Well, that's because we hit it with a negative and it flipped it over the axis. So let's start with a equals -6. And we've already solved for w, so what's our equation? D equals -6 cosine of pi over 2t. And there we go, right? So we already solved for the w before. The period was 4. Set 4 equal to 2 pi over w, and that'll solve for that w. All right, the last little thing to discuss here is frequency. So the frequency is the reciprocal of the period. So if the period of a cosine function is 2 pi, the frequency is 1 over 2 pi. A little description here, it says it tells you how many complete cycles you get per unit of time. So if you get 1 cycle of the cosine in 2 pi, then every second you get 1 over 2 pith of the cycle. So there was my example. If the period is 2 pi, we're measuring in seconds. It takes about 6.28 seconds to complete a cycle. So how much of the cycle could you complete every second? You'll complete about 0.16 of the whole graph. Right? Multiply that by 6.28, and you'll get the whole cycle. Now, where do we use frequency? Any kind of radio waves are based on frequency. So FM waves are measured in megahertz. Right? You ever look closely at a radio, let's say in your car, you see an MHz. That stands for megahertz, millions of cycles per second. So those waves are oscillating pretty quickly. Those waves are delivering the radio signal, and it's oscillating at a certain frequency, and that's how your receiver knows how to lock onto that frequency. So suppose the station's broadcasting at 94.5 FM. That means that the transmitter, or something in the transmitter, is oscillating how much? 94.5 million cycles per second. So you can actually write an equation for the simple harmonic motion of the radio waves. Okay? Multiply the frequency by 2 pi, and you'll have that W. So these are going to be massive numbers, but this is what goes on in transmitter sites and radio towers around the country, and that's how you get those FM radio waves. AM is something different. In AM, instead of the frequency modulating, it's the amplitude that's modulating. So AM instead of FM. So suppose there's a radio station, 99.1 FM. It's got radio waves with a frequency of 99.1 million cycles per second. So how do we write an equation for that? Well, first of all, we're going to use sine. So D equals the sine of some W value times T, simple harmonic motion of the radio waves. So how do we get that W? Well, this simply says multiply the frequency by 2 pi. So the frequency is going to be 99,100,000. So 99.1 million cycles per second, right? That's the megahertz part. Multiply this by 2 pi, and that's your W. So was 99,100,000 times 2. Your W is 19820,000. 198 million pi. Right. So my equation is the sine of 19820,000 pi t. Okay. And that will give you the simple harmonic motion of the radio waves for a station that's broadcasting on that frequency. So I just think it's an interesting connection, right? You walk into a store, you turn on the radio in your car, and you hear something on FM or AM, and you hear FM. What does it mean? What is it that's the frequency modulation? That is what frequency is. And we can write equations for that based on the information we already know. Pretty cool.